is 1.1. Okay. Use this division algorithm to find the HCF of the two numbers 135 and 225. Okay. We all know that before starting HCF, the first step is to identify which is the larger number among the given two numbers. Okay. I can easily find that 225 is the larger number when compared to 125. Now we want to write larger number in terms of smaller number into coefficient plus remainder. Hence I can write 225 in terms of 135 as 225 is equal to 135 into 1 plus 90. I can write 135 in terms of 90 as 135 is equal to 90 into 1 plus 45. I can write 90 in terms of 45 as 90 is equal to 45 into 2 plus 0. In this step we find that remainder r becomes 0. Hence in this step in which the value of b, that is 45, is considered as the HCF for the given numbers. Okay. Another problem. Find HCF of 196 and 38,220. Okay. Again the first step is we have to identify which is the larger number in the given numbers. I can clearly say that 38,220 is the larger number when compared to 196. So now I can write this 38,220 in terms of 196 as 38,220 is equal to 196 into 195 plus 0. Here for the first step itself we get the remainder 0. Hence the divisor 196 is called the HCF of the two numbers 196 and 38,220. Okay. Let us see another sum. Find the HCF of 867 and 255. Now again the first step we have to do is identify the larger number, that is 867 in the given two numbers. Okay. Now I want to write this 867 in terms of 255 as 867 is equal to 255 into 3 plus 102. I can write 255 in terms of 102 as 255 is equal to 102 into 2 plus 51. Okay. I can write this 102 in terms of 51 as 102 is equal to 51 into 2 plus 0. Hence in this step we find that the remainder becomes 0. Now the divisor 51 is become the HCF of the given two numbers 867 and 255. Okay. Second problem. Show that any positive odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Okay. We all know that the general equation of user division algorithm is a is equal to bq plus r, where the range of r lies between 0 less than or equal to r less than b. Okay. Let us consider a be any positive odd integer and the value of b is equal to 6. When you substitute b is equal to 6 in the general equation, we get a is equal to 6q plus r, where the range of r lies between 0 less than or equal to r less than 6. That is, the value of r is r equal to 0, r equal to 1, r equal to 2, r equal to 3, r equal to 4 and r equal to 5. When you substitute all the r values in the above equation, we get a is equal to 6q, a is equal to 6q plus 1, a is equal to 6q plus 2, a is equal to 6q plus 3, a is equal to 6q plus 4 and a is equal to 6q plus 5. Okay. This is the mixture of both even integers and odd integers. But in the question they were asking only about positive odd integers. So I want to eliminate even integers from the mixed integers, so we get odd integers. Okay. So I can clearly say that a is equal to 6q, a is equal to 6q plus 2 and a is equal to 6q plus 4. These three terms are even integers. Why? Because these three terms can be divided by 2 and the remaining 6q plus 1 and a is equal to 6q plus 3 and a is equal to 6q plus 5. These three are positive odd integers. Okay. Third sum. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to be marched in the same number of columns. What is the maximum number of columns in which they can march? Okay. In this type of questions, what we have to do, we want to find the HCF for the given two numbers, that is 616 and 32. Okay, for finding HCF, what you have to do, first we have to identify which is the larger number in the given two numbers. I can easily find that 616 is a larger number when compared to 32. So I want to write 616 in terms of 32 as 616 is equal to 32 into 19 plus 8. Now I can write this 32 in terms of 8 as 32 is equal to 8 into 4 plus 0. So now in this step we find that the remainder becomes 0. So now the value that is multiple of coefficient, which is 8, is the required maximum number of columns in which they can match. Okay. Fourth question. Use useless division lambda to show that the square of any positive integer is either in the form of 3m or 3m plus 1 for some integer m. Okay. Now we all know that the general equation of useless division lambda is a is equal to bq plus r, where the range of r lies between 0 less than or equal to r less than b. Okay. Let us assume that a be any positive integer and the value of b is equal to 3. When you substitute b is equal to 3 in the general equation, we get a is equal to 3q plus r, where the range of r lies between 0 less than or equal to r less than 3. That is, the value of r is equal to 0, r equal to 1 and r is equal to 2. Okay. Now we have to substitute r is equal to 0 in this above equation. We get a is equal to 3q. Squaring on both sides. Why we are doing squaring? Why? Because in this question they are asking to show that the square of any positive integer. So we want to find a squared. So we are doing squaring on both sides. We get a squared is equal to 3q whole square. That is, a squared is equal to 9q square. I want to write 9q square in terms of multiples of 3, so that it becomes a square is equal to 3 into 3q square. Now I consider this 3q square is equal to m, then it becomes a square is equal to 3 into m. Okay. Case number 2. R is equal to 1. R is equal to 1. If r equal to 1, then a becomes 3q plus 1. Again we are doing squaring on both sides. So now a square is equal to 3q plus 1 whole square. It is in the form of a plus b whole square. We all know that a plus b whole square is equal to a square plus b square plus 2ab. That is, a square is equal to 3q whole square plus 1 square plus 2 into 3q into 1. That implies a square is equal to 9q square plus 6q plus 1. Again I want to take 3 as common in these two terms. Now it becomes a square is equal to 3 into 3 square 3q square plus 2q plus 1. Now I am treating this 3q square plus 2q as m. Now I get a square is equal to 3 into m plus 1. Okay. Case 3. If r is equal to 2, that is, a is equal to 3q plus 2. Again squaring on both sides. We get a square is equal to 3q plus 2 whole square. It is again in the form of a plus b whole square. That is, a square plus b square plus 2ab. That it becomes a square is equal to 9q square plus 12q plus 4. Again I want to take 3 as common in all these three terms. Then I get a square is equal to 3 into 3q square plus 4q plus 1 plus 1. So if I multiply this, I get the same result. Okay. And now I am treating this 3q square plus 4q plus 1 as m, so that I get a square is equal to 3 into m plus 1. So from all these three cases, we can clearly say that the value of any positive square of any positive integer is in the form of 3m and 3m plus 1. Okay. Use this division lambda to show that the cube of any positive integer is of the form of 9m, 9m plus 1 or 9m plus 8. Okay. We all know that the general equation of Euler's division lambda is A is equal to BQ plus R, where range of R lies between 0 less than or equal to R less than B. Okay, now let us consider A be any positive number and the value of B is equal to 3, then it becomes A is equal to 3Q plus R, where the range of R lies between 0 less than or equal to R less than 3. That is, the value of R is equal to R equal to 1, R equal to 2 and R equal to 0. Okay. Now, we are considering the first case, that is R equal to 0 in this general equation. Then we get A is equal to 3Q. Now, cubing on both sides. Why you are doing cubing on both sides? Why? Because in the question, they want to show that the cube of any positive integer. That is, they were asking about A cube. So, for converting A into A cube, we are doing A cubing on both sides. So, we get A cube is equal to 3Q whole cube. That implies A cube is equal to 27Q cube. If I want to write 27Q cube in terms of multiples of 9, then A cube is equal to 9 into 3Q cube. Now, I am considering this 3Q cube as M, then we get A cube is equal to 9 into M. Okay. Case number 2, if R equal to 1, then Q is equal to A is equal to 3Q plus 1. Again, cubing on both sides. Now, we are getting A cube is equal to 3Q plus 1 whole cube. It is in the form of A plus B whole cube. We know that A plus B whole cube is equal to A cube plus B cube plus 3AB into A plus B. So, A cube is equal to 27Q cube plus B cube, that is 1 cube 1, plus 3AB, 3 into 3Q into 1 into A plus B, that is 3Q plus 1. Now, A cube is equal to 27Q cube plus 27Q square plus 9Q plus 9. Now, from among these three terms, I want to take 9 as common. So, A cube is equal to 9 of 3Q cube plus 3Q square plus Q plus 1. Okay. Now, I am considering this all the terms in the bracket as M. That is 3Q cube plus 3Q square plus Q as M. Then I get A cube is equal to 9M plus 1. Okay. Third condition. If R is equal to 2, then A becomes A is equal to 3Q plus 2. Again, cubing on both sides, we get A cube is equal to 3Q plus 2 whole cube. That implies it again form of A plus B whole cube. So, we know that A plus B whole cube is equal to A cube plus B cube plus 3AB into A plus B. So, A cube becomes 27Q cube plus 4 plus 3 into 3Q plus 2 into 3Q plus 2. Now, it becomes A cube is equal to 27Q cube plus 54Q square plus 36Q plus 8. So, if I want to take 9 as common from above 3 terms, then I get A cube is equal to 9 of 3Q cube plus 6Q square plus 4Q plus 8. Now, I am treating all these terms in the bracket as M. Then I get A cube is equal to 9 into M plus 8. So, by all these three cases, we can clearly say that for cubing of any positive integers is in the form of 9m, 9m plus 1 and 9m plus 8. Okay.